Ever wondered how AI deciphers the invisible threads connecting our world? Like tracking disease spread through social networks, mapping protein interactions in your cells, or even tracing cinematic relationships between actors and directors. Today, we're diving into a revolutionary approach to graph analysis. GEFRFE, a breakthrough method that's redefining how machines understand complex networks. Let's unpack this innovation step by step. To start, let's define a graph. Think of it as a mathematical representation of relationships, cities linked by roads, people connected on social media, or molecules bonded in a chemical structure. But here's the challenge. Traditional AI struggles to process these networks intuitively. That's where graph embedding comes in. It's the process of converting these abstract relationships into numerical vectors, essentially, a language machines can analyze. These vectors capture not just individual nodes, but also their contextual relationships, like how a person's position in a social network influences their influence. However, older methods often miss critical patterns. They might highlight obvious connections but overlook hidden structures, like missing a key bridge in a road network. Enter GFRFE, a technique that acts as a multi-layered microscope for graphs. Instead of analyzing a single frequency of a network, it explores a continuum of perspectives, revealing secrets buried in the data. So how does GFRFE work? At its core, it leverages the Graph Fractional Fourier Transform, GFRFT, an advanced variant of the Fourier transform you might recall from signal processing. While the traditional Fourier transform decomposes signals into frequencies, think of it as breaking a song into individual notes. The GFRFT allows AI to tune into different layers of a graph structure. Imagine adjusting a telescope to focus on specific regions of a starry sky. GFRFE does something similar for networks, revealing patterns at varying scales. The real innovation lies in combining GFRFT with fractional domain filtering. This process uses a parameter called fractional order, alpha, to control how deeply the algorithm probes the graph. By adjusting alpha, GFRFE can highlight dense clusters of nodes, detect long-range connections, or even isolate anomalies. Researchers tested two strategies to optimize this: a grid search, systematically testing all possible alpha values, and an adaptive neural network, a self-optimizing system that dynamically selects the best alpha. The results: GFRFE outperformed existing methods across 6 real-world datasets. On the proteins dataset, it improved accuracy by nearly 10%, while on IMDB-MULTI, it achieved a remarkable 33%, a leap in performance for AI. Crucially, it maintains speed comparable to older techniques, proving that precision doesn't have to come at the cost of efficiency. Why does this matter? Imagine AI accelerating drug discovery by mapping protein interactions, optimizing urban traffic by identifying hidden bottlenecks, or enhancing recommendation systems by uncovering subtle user preferences. GFRFE isn't just a technical advancement, it's a tool for solving real-world problems with unprecedented depth. As graph data grows more complex, methods like GFRFE will be critical for unlocking insights we've yet to imagine. The next time you see a social media trend, a medical breakthrough, or a cinematic connection, remember, AI is decoding these networks one layer at a time. Stay curious and keep exploring the frontier of machine learning.